Right, let's see how this thing works. Cool. It's got buttons. Right. So, I'm Jordan. How's it going? I'm a software developer at Branded3, and I lead the search and analytics platform. Our stack mainly consists of C#, that runs on Mono, some PHP, we're trying to run it on Hip-Hop VM, which is Facebook's virtual machine. We write quite a bit of JS as well on Node. We're starting to use a lot of Node for a lot of asynchronous stuff over some WebSockets, which is quite cool. And we kind of try and use whatever we want in terms of if it works and if it fits, then we'll use it. If it doesn't, and we're just trying to be cool and try and be hipster, then no, we're not doing that. This talk's really about my journey really into the world of big data and NoSQL technologies, and it's really a culmination of my learnings over the last several months. I guess what I'm going to talk about is the decisions I've made with regards to choosing a suitable technology stack for the data that we're going to be, that was put forward. Making architectural decisions around structuring the data for performance. The hardware-wise, we needed to make sure that the data was pretty much structured for like reads, writes, and just shot off the bat as quickly as possible without just relying on the hardware, because we're running on a lot of just basic X-Enterprise level dedicated machines in our own server room. So we wanted to make sure that our data structures, our databases, our technology stack really suited to the kind of position we were in. And with that, we looked at future-proofing and scaling solutions because from what I've seen, I guess if you take Facebook, for example, they went with MySQL and PHP to start off with. They shot up and rose to like hundreds of million users, and they thought, oh crap, we've used PHP and MySQL, we're screwed. So they have like teams that are dedicated literally to making sure MySQL's performance is at the top. They have people that are re-engineering MySQL. They have people that have rewritten the MySQL parser to allow for memcache queries on top of it, and that's not really something that I wanted to be doing straight off the bat. Without further ado, I guess, the first question would be, what's our infrastructure like? And it really narrowed it down to three things. Over the last several months, it kind of occurred to me that we have three problems. The first one is data storage. The second one is processing, and the third one is infrastructure. With data storage, that's more what we're using to store our data and how we get it out. The processing side is more to do with concurrency and parallel processing all our tasks over a Linux cluster that we've got. And then we have infrastructure, and generally speaking, people think of infrastructure as, well, you've got your network, you've got your hardware, but infrastructure for me really was something to do with how we process our data and what we're using to process our data. So we run a lot of our C# on Mono, and that's more for, I like Linux, I've been brought up on Linux, but I also love C#. I was introduced to it about a year and a half ago, and over Java, over potentially some dynamic languages, it really fit what I wanted to do with the back end and processing data. And all these kind of technologies, they're encompassed in our infrastructure. So we use RabbitMQ, everything runs on Linux, but we actually have to develop on Windows, which is a bit of a shame, I'm sorry to say. And so our three tiers kind of look a little bit more like this. Our processing and our data storage are completely contained within our infrastructure, but not just on a hardware level, it's also on a software and a stack level. So with that in mind, the second question for me was, what is big data? And the definition of big data really, it changes. Generally speaking, it's large amounts of structured and or unstructured data. And the volumes can range from 100 gigabytes to petabytes of data. But it can vary between company to company. Traditional relational databases might struggle to allow you to effectively get information, and that's not data, that's actually compiled information that you want to see on your screen, out quickly. I mean, you could fill a MySQL database, a single table with 10 million rows of completely irrelevant data, and that might fit. But really, if we had hundreds of tables, hundreds of millions of rows, how quickly can we transform that data from the data that it is to the actual information that we want to see on the screen? And like I said, it varies depending on the application that you're building and the company that you're in. Generally speaking, big data isn't just massive amounts of data. If you look at Facebook, it is massive amounts of data. They have the largest publicized Hadoop cluster. That's about, I think in 2013 it was 300 petabytes. This isn't the top two, by the way. Just two kind of familiar faces. So LinkedIn have a 40 petabyte cluster, and they release, like with Facebook, they release a lot of open source software for Hadoop and various other platforms. That is real big data, and by no means is our current application at 300 petabytes or 40 petabytes or even a petabyte. It's a couple of terabytes right now, but really the key thing is it's not just about size. It really isn't. I know a lot of people say that about a lot of different things, but with big data, it's not just about size. It's about what you're doing with the data, whether or not you're analyzing it for whatever reason, mining it, trying to visualize it on the screen. It's more about your tool set. What tools are you using to dig down into the data? How fast can you analyze that data? And from my point of view, when I came to build this system, and this system is basically search analytics, I needed to kind of weigh up the options. And my third question was, what is NoSQL? SQL structured query language. Generally, that's associated with relational database systems. And with NoSQL, you have a look around. What are they? They're generally speaking built to scale large volumes and aid in distributed processing. And you get multiple different types. You get column-based stores, you get document stores, graph stores. If anyone's ever had any dealings with the Facebook graph, that's the best example of how a graph store would look. You have different, effectively objects that relate to different objects, and you can pull them out. But I'm not really going to focus specifically on what types of NoSQL databases there are. Most of them are schemaless in the sense that you don't have a defined structure that's on a database level, and you also lose a lot of aggregation functions, so lots of joins and features that are common to relational databases. So, MySQL, Postgres. Where I entered the big data scene, I guess, was when one of my colleagues said to me, "Hey Jordan, come check this database out. It's 2 terabytes, and you'll be taking it over." And I said, "Cool, this is awesome, loads of data." And then he said, "I'm leaving in a week." And I literally crapped my pants, because for me, I was this PHP developer working on CMSs. I'd never done anything with Microsoft SQL Server. I'd never done anything with C# at the time. And he was just like, "Yeah, good luck." Okay, cool. That was my face. I literally, completely blank. I had no idea where I was going to go. I had no idea what I was going to do. My first thought at the time was, yeah, let's move all this to AWS. I had no idea what that meant. So I thought, what have I got? I've got a database with Microsoft SQL Server, storing almost 2 terabytes of data. It had 8 gig of RAM and 4 cores, which was completely pathetic for what it was trying to do. The queries could take anywhere between 15 and 45 minutes, and that's for actually getting data onto the front end. Two of the biggest tables had 700 million rows and 300 million in 500 gigabytes and 300 gig. And they were the biggest problem for me in terms of querying. Even doing a count on that table took 16 minutes. There were many other tables with multiple millions of rows in it. Most of them, were split out over three databases, with a few that had hundreds of columns in. And I didn't want to go with the Microsoft SQL solution anyway, because for me, I really knew that there were other technologies out there, even Postgres, for instance. So I knew that if I was going to go with a SQL solution, something with a structured schema, I'd be effectively taking all this data and trying to remap it out. And that, for me, was not, for one person at the time, was not going to happen, in the space of time that management wanted. They're literally like, look, we've got this database, we've got all this data, like, let's see it on the screen now, I want to see it. I want reports out of it, I want this, I want that. And, I just wanted to go into a little corner and cry for quite a few weeks. But at the time, it seemed like a mammoth task. I took a step back from that, for instance, and said, let's be pragmatic about it. We need something that can store this much data from the get-go. It needs to be capable of handling the exponential increase of data that we're going to throw at it. The more stuff we wanted to analyze, the more data we'd take in, the faster. It needed to basically consistently be fast. My second point, really, that I asked myself was, is a relational database right for this solution? Right for me, right for one developer to take over? And how much time am I going to have to spend operations side? How much time am I going to have to spend setting it up, managing it, firefighting when things fall over? And from what I'd heard from, obviously, blog posts from Facebook, big data, even though it didn't really apply to me in the sense that I don't have 300 petabytes of data, I wasn't going to be naive enough to say, yeah, let's use MySQL and just hit the problems when we get to it. So we looked at MySQL anyway. Partitioning data really, at the time, for me, it looked like it wasn't going to be easy. And partitioning from a performance point of view was a big deal. We're bound by these schemas and linear tables. So I'm going to have to be creating databases. I'm going to have to be creating tables. I'm going to have to be creating columns. Yeah, we can use an object, object relational mapping system. But really, what kind of performance hit is that going to take on our system? Replication, failover. Does it have transparent auto failover? The ops team at Facebook, they said it was a full-time job managing that kind of stuff. Maintaining it could potentially be a full-time job pretty much from the get-go. Not okay. I want to be writing this application and making sure that the code reflects the performance tuning of the data layer. Something else that really caught my attention was I watched a MongoDB talk that a lead developer at Craigslist did at Mongo San Francisco. And he said that he said that he had 2 billion records in one of his archive tables, and it took 2 weeks to alter the schema. He literally issued an alter table command, and it took 2 weeks. No, we're not going to be doing this. But then, as I was thinking, no, we're not going to be doing this, he then said, oh yeah, that was on the master. We've then got several slaves to replicate over. So what went from a 2-week, alter table on a master turned into a couple of months worth of replication over to slaves. I wasn't going to take that chance at all, especially with the fact that one of our tables had 700 million records in already. Literally, get the fuck out MySQL. The next thing I did was take a step back and look at all the technologies that are around. And yes, I did include MySQL in this, and I did include Postgres. But for me, the other types of database that were coming along, I know Facebook used Hadoop, Twitter up until recently used Cassandra, so they were 2 big contenders. But then I also had a quick look at Ryak, Couchbase, Neo4j. HBase sits on top of Hadoop, but it's kind of a separate beast. And I narrowed it down to Hadoop, MongoDB, and Cassandra, and that's purely because of the good things that I'd heard of, happenings with Twitter, Facebook, and all the big companies that are dealing with huge amounts of data. Even though, like I said, I knew my data set wasn't going to be that big, or it potentially could be, it depends how far we take this platform. I knew that I knew that with these technologies I had a lot of room to breathe. The reason MongoDB's in there is because from the get-go, like I said, it popped up. It popped up so many times when I was looking through different solutions for NoSQL stores. So if we had a look at Hadoop, Hadoop is basically, some people band Hadoop around. You say, oh yeah, we're going to use Hadoop for this and we're going to use Hadoop for that, but really Hadoop is 2 things. It's a distributed file system, and that manages data redundancy and being able to take these chunks of data and send them to the map and reduce the map reduce system, which is the second part. And the map reduce system effectively is a distributed processing framework, which allows you to split up a huge file and send chunks of it and run algorithms over it and get an output. Can we just use Hadoop on its own? From what it looked like, no. That was a big downer straight away. We need some kind of other system to store the output in to be able to directly query in real time all this data. What was the learning curve like for one developer? Probably getting up and running. It might be fairly simple, but how much do I really know about Hadoop and how much is available to me literally on the screen right this second from a documentation point of view? No, I mean, looking at how much data it can actually handle, it's definitely a brilliant solution. Potentially good for the long-term aspect of this platform, but right now it's not. It's something that I'm just going to have to steer clear from. If we look at Apache Cassandra, I'd heard a lot of good things about Cassandra from the Twitter sphere. Twitter specifically were using this up until recently for their tweets and replies table. It scales across different locations very well. It's got a peer-to-peer based engine that allows you to actually replicate over data centers very well. Actually setting it up in a cluster is literally a 5-minute job. It's got its own SQL-like query language called Cassandra Query Language, which is kind of obvious. The dynamic schema options for Cassandra were also good. So we could effectively create what looked like a table. It's actually called a key space that had specific columns in that we could load our data in, but we weren't bound to those schema choices. It was actually, and even now, it's still a very good option. It's something that I'm potentially going to look into to scale one of our bigger tables over to in the next 6 months, depending on what Hadoop and HBase offer. But I think the reason I didn't go for Cassandra right straight away was because I didn't really know much about column-based stores at the time. And performance tuning, the learning curve of that performance tuning, for me, it wasn't right there on the page. Now, if you look at like the Apache website and look at Cassandra, there's a lot going on. I started this project at the back end of 2013, but didn't get like properly into it up until about 2 or 3 months ago. The interoperability options with different technologies actually were really good as well. So we use C#, like I said. We also use PHP. It has drivers for them. Generally speaking, I think most of those drivers aren't the official drivers, but obviously GitHub is the best place to go for these kind of things, and I did, and there was plenty out there. The documentation and community support looked to be good as well, but the time to live for me was the biggest deal, and I really wanted to get up and running as quickly as possible because every day the system wasn't up and running, I was losing data, and for me that wasn't really an option, especially from the management pushing down on me. I needed to kind of say to them, yes, I've got a solution, we can get this up and running very quickly. I looked at MongoDB, and I guess, I don't want to seem too biased towards it now that I've used it, but it had this dynamic schema that's document-based, out-of-the-box replication and sharding, which meant performance-wise and redundancy-wise, I could get all this up and running, and I did this quite recently when I added some new replica sets in front of Andy Hathaway over there in about 5 seconds, and it was just replicating. Obviously, you've got to set up the servers, but you did it in a couple of hours tops, including the replication time of about, I think we replicated one of the tables over and it's 40 gig, and it did it very quickly over our gigabit network, which isn't really that fast. The JavaScript engine that allows you, the Mongo shell has a it's based on V8, which if anyone's a JavaScript developer, it's very easy to get up and running with. You can even kind of write your own Mongo RC kind of scripts that you can load directly into the shell and effectively have special functions that can quickly automate tasks for you inside the database. It had a large number of supported drivers, ticking the box right there, and the documentation and community support was excellent. One of the first talks I watched was that MongoDB talk on Craigslist, and he went through some key things that I was looking for. So right from watching a 30-minute talk to reading the documentation, I knew how to shard a database, I knew how to replicate a database, I knew what the best sharding options were. I knew what data I had already, so I could quickly transpose all these theories over to my data and create a practical outset for it. The time to live, like I said, it looked great. It's built a large amount of data. So MongoDB, they say, comes from the word humongous. Fair enough, I'll go with that. Migration possibilities for the future. Because MongoDB actually stores all your data as JSON, getting out of the database and then transposing it over to something else was potentially a very easy thing to do. So if I wanted to take my MongoDB table, which was one of them that's 40 gig, I could load that into Hadoop if I wanted very easily, and then run MapReduce over it if I needed to. So there's an option there, and it's even got a built-in Hadoop adapter. So I've got potential long-term solution and a mid-term solution that could potentially be a long-term solution that can feed directly into a long-term solution. So they all tick the box very well. And it looked like we could get up and running pretty much, within a couple of weeks to just getting some of the core data that we needed to analyze in. That slide should definitely not be there. So we chose MongoDB, and I'm kind of going to go through how we structure our data in MongoDB and take the relational. I'm going to give you a simple example of a relational system and transpose it over to the MongoDB kind of infrastructure. So we denormalize our data, and what you would do with a relational system is you'd normalize that data. So if you take a simple blog, for instance, in MySQL you'd need a post table probably, a users table because users have posts, a comments table, potentially a tags table. In MongoDB you just need a posts collection. If we look at the relationship in MySQL, it would probably go something along these lines where you've got a users table which has a user ID, post table, and then there's a relationship between the IDs there. And then, as you can see, there's a post and tags and comments. You'd need potentially these columns in these tables. So you've got in the user table, like I said, user ID, name, post ID, post body, comments, and comment ID, post ID. And you've got to really, build the relationships between these tables. In MongoDB, my blog post just looks like this. It looks like effectively a JSON. It's just a JSON object. And you've got your title, your body, your comments are actually embedded sub-documents, the same with tags and users. Effectively, everything, all the information that you would have in your relational database is all within one document. And this is actually like a very simple example. Like I know you could obviously have problems with potentially if you update a username, you update comments might have users, but really, this is kind of the model you should be leaning towards from a document store perspective. But what that meant was, it allowed us to better form our data layer to the application layer, and our schema ended up being our code, our objects. And we didn't need to run any migrations when we changed these. Brilliant. The fact that we used MongoDB for this as well meant we had one collection, that would be one query. There would be no aggregated queries to any other table, so no extra overhead. There'd be less overhead mapping the data layer to the application layer. I know it could be minuscule depending on how fast you're processing the data front-end wise, but you didn't really need to do any processing. It was already there. There's less time making your database, which was great. The only thing you need to realize with this is because you've got a dynamic schema doesn't mean you don't have a schema at all. It can really affect performance. So, like I said, with that simple example, you would potentially run into performance problems when you start to do more complicated things. That's fine. You adapt. More complex document structures, which is what we went for, we started creating buckets of data. So we had data that was associated with days, lots of small chunks of data that was associated with a single date. And what we ended up doing was taking these days and sticking them in a bucket. And each bucket was based on a week. And each week had about 7 days. And they contained thousands of items, which meant, like I said before, it meant one query would get us a shed ton of data out. We can also index on these subdocuments as well. So indexing is a big thing. When your database starts grinding to a halt, everyone goes, well, have you added any index? And the developer will go, what are indexes? And you'll just facepalm. The thing about MongoDB here is the ability to index on subdocuments. When we didn't need all these extra tables that we needed to optimize, we could literally optimize on one single collection on the fields that we needed to be querying against. MongoDB right now has a 16 megabyte document limit. Our biggest document has about 7,000 objects in it, which is about 4 meg. So we're well within our we're well within our kind of size restrictions. The other thing that really caught my attention as well was when using these buckets, some people would say, well, if you're pulling out 7,000 objects and you only want one object, that's a lot of overhead, that's a lot of network bandwidth to be pulling, you know. That could be 4 meg when you only need 1 KB. Okay, well, MongoDB allows us to select which objects within the document to return. So I had an issue straight up when I was literally querying for these buckets and checking them. I was just checking if they existed, and it was taking 200-300 milliseconds to just pull a single document out. When you've got millions of them and you need to go through them all, well, performance issues. So I had a quick look in the documentation, which, like I said, everything's in there, and I managed to limit my documents. I nicked 250 odd milliseconds. I think I managed to get it down to 10 milliseconds to be able to take these buckets out and check that they existed. And right there I have literally one collection. I have a whole application that can pull a load of data out, but with one collection. So with that in mind, buckets of data, they're very good from our point of view. But the initial version of the system with MongoDB, it started to grow documents. So growing documents is where, effectively, you end up with performance issues. And what MongoDB does, really, is it allocates on disk like a section of the page file, which is effectively the file that stores all your data on disk. And what happens is, when you add a document or insert a row, or effectively rows of documents here, into MongoDB, it allocates some space in the file with a little bit of padding. So what that means is, your document goes in nice and snug, it's got a little bit of space if you wanted to add new fields to it, but when you exceed that padding, you end up with problems. And those problems occur when MongoDB decides, right, you've exceeded all your padding, we're moving it to a different place in the file on disk. That's very expensive. So the initial system that we built had to basically do 2 million updates in the space of under an hour. And these 2 million updates were effectively pushing loads of data to those buckets. And because there were small chunks of data for a day, and we had these weekly buckets, you know, it seemed like a good idea at the time. And to start off with, the performance was brilliant. So you get to your first week, it's Monday, we start inputting all the data into this bucket and growing, the performance is brilliant. We're getting, based on some network I/O, we're getting something like in the region between 2,000 and 10,000 updates a second, which is great. And then Tuesday, it's not 10,000, 8,000, it's 6, okay, maybe, I don't know what's really going on here. We'll just wait. And then by the time Friday came around, there was nothing literally updating. Something that should take less than an hour was effectively, could have taken 2 weeks. And again, Craigslist came to mind, and I thought, this is not happening. This is absolutely not happening. So the documents began to grow at an alarming rate, and because the analysts were adding so much more data into the system, that exponential increase really increased the entire data set and increased the throughput we needed to achieve, and everything just ground to a halt. We revised the system, and we basically took all these small chunks and we loaded them into a raw collection. MongoDB is extremely fast for writes. It's brilliant, especially using batch insert. And then we had effectively a cron. It wasn't really a cron, it was we've written a framework to do all our parallel processing at different intervals. That it runs at a certain interval, so for instance, this runs every day. And what this does is takes all the data for that single day, for that potential ID, and compiles that data into a single date. So that like I said, there was 7,000 objects in one of those buckets that spans 7 days. We took the day's data and compiled it into the 300 to 1,000 objects we may have in that single object. And then we threw it into the bucket. It reduced the page loss massively. It managed to do it in something that I was looking at that I thought would take maybe 30 minutes. It did in 5. It was super fast compared to that initial version. Like I said, the initial system just grew these documents. So, with that in mind, we had a system that was taking in all this data and being able to store it, and being able to, and we actually ended up being able to get it out very quickly as well. So, because MongoDB had this JSON-based document schema, we managed to prototype a JSON API that just took MongoDB fields as queries. And the JSON API literally fell out of my computer. It was great. I managed to get something up in about 2 hours, which could have taken days. And getting the buckets was ridiculously easy. And we used, I guess, the overhead that we actually had was taking the data out and then processing over potentially some of the date objects that MongoDB throws out because they're not standard. But really, that was our only overhead. It really, for me, it allowed me to focus more on the processing, more on the data structure that I might be implementing in the future to, like, it literally allowed me to do that straight up. And the scaling side of things as well is, I managed to prototype all the sharding, all the replication in the space of a week, while the thing was growing at an alarming rate. And by that I mean, when I say I prototyped it in the space of a week, I took a load of VMs and I wanted to see how easy it was to replicate and shard data. And it was literally, I got everything up and running within 1 day. But what I wanted to do was start testing it. So while my data was collecting, I was testing more of MongoDB's functionality, and then I knew that I could come back to all these buckets, and if I needed to move them around, change the schema, I could do that in code. The key points really for me were the speed of which we could get up and running. We got to our data as fast as we were putting the data in. It could handle terabytes of data from the get-go. We also had the scaling and redundancy options already sorted out before we even needed them. And at the time, it was actually just me. The other issues I had to deal with, though, coming up to kind of tens of millions of rows in a single collection, indexes of, like I said, you can index on subdocuments, but you need to really look at your data access patterns when you're basically figuring out what the best way of getting to data is. So I took some time to revise the indexes, and I took some time to make sure that the way we were accessing our data was suitable to the indexes that we had on the collections. Indexing in MongoDB is really easy. I guess with MySQL it's really easy to do. You just hit add index on a field. The page fault issue. So when we were growing documents, the page faults which caused the disk I/O to just skyrocket, we managed to mitigate that really easily by using solid-state drives. The other thing I noticed, though, was when MongoDB allocates padding, it doesn't have to use all that padding, but when that padding's there, it's using up space, and after maybe 3 or 4 weeks, your bucket's stale, and you've got all this padding that's potentially accumulating gigabytes of data. So growing documents actually has a really negative impact on space efficiency, and that's something that I figured out how to deal with, but right now it's actually a small issue in terms of fixing it, because to do that I'll need to basically perform an operation on the database which will incur a global write lock, and depending on how much data is in that collection, in our case the one that I want to trial it on is 40 gigabytes, that could take, I don't know how long that could take, which worries me. Fortunately, what I can do, though, is with MongoDB's replication facility, I have an entire copy of the entire sharded cluster on a separate set of machines. I can take these out of the loop, try it while the primaries are still doing their work, see how long it takes, and when I'm done, bin off my replica sets and resync them. Things work best when they're in memory. I think that goes without saying for any database. Looking at the way you access data is really important. What kind of data should be in memory? So should the data from a year ago be in resident memory right now when you're trying to access data for the relevant days? Probably not. Based on some new systems that we've put into place, we can actually do ad hoc analysis on these entire raw stores. We actually do need to keep these indexes on all the data. But for other collections, we can actually shard out the collections themselves on a single database server and only create ad hoc indexes to get the data out when we need, which actually conserves memory ridiculously well. If you're lazy, use SSDs. It won't save you forever. And something I'm kind of slightly worried about now is how long are our solid-state drives going to last with so many writes going to the database. Solid-state drives have a finite amount of writes even. And for me, even in a RAID configuration, even with other configurations, so it's a worry. It's not a huge worry because I know my data is backed up. I know I've got loads of replica sets with all the data on. But again, that's ops time, and I don't want to be dealing with that. So, to summarize, dealing with large amounts of data may warrant a NoSQL technology, but it may not. It really depends on what you're going to be doing with the data. You need to use them effectively if you're going to use them, and structure your data that best suits you, your access patterns, processing patterns, and also the actual database you're using. If I stored my entire data set in one document, not that that was possible because of the 16 megabyte limit, that would not be the best way to use MongoDB. And there's quite a few things online where you can actually see that you can see how Twitter would handle against MongoDB and what kind of different structures of data would benefit, for instance, like fanning out for a message system. So you could build like an inbox system that, almost like Facebook's instant chat system. How would you best suit MongoDB to perform against that? Because it will handle it. You've just got to make a few sacrifices, and those sacrifices really come with how much space you're using. Schema's really important, no matter what. It's a big sigh for me because I hate schema design. I spend 60% of my time now looking at how I'm going to build up my data objects and how to better improve the objects in the system. Know the technology that you're using well. Okay, like I said, MongoDB's documentation is it's brilliant. I can find everything I need, and if I can't find it, Stack Overflow, right? There's more than one way to skin a cat. You don't have to use MongoDB. I'm kind of being an evangelist here because I love it, but I really am considering Cassandra, and that's because I know that people like Twitter, the teams at Twitter have scaled a lot of data. I'm dealing with a lot of data from my relative point of view, but that can scale a lot of data. Yes, they switched, but am I really going to get to as big as Facebook or Twitter, in the space of a year? Maybe not. I guess that really covers everything. Does anyone have any questions about big data?